Thank you.
Can I go?
And hold on the very top button.
Oh, I see. Gotcha. Okay, can people hear me okay?
Yes.
Great. Yeah, thanks for having me. Thanks everybody for being here. And I should also thank specifically my colleague Daniel, who did most of the heavy lifting for making these slides. So thanks to him as well. So I'll start with a motivating question, which should hopefully explain the title of my talk. So the question is this: yeah, what's the smallest number of clues that I need to determine a Sudoku puzzle with a unique solution? And the answer turns out to be 17. So here's an example. And this was proved, I guess, in 2013 via basically an exhaustive search over 16 clue Sudokus. And here's an example of a 17 clue Sudoku. So if you're bored and your brain still works, you can work on this for the rest of the talk. But it naturally generalizes to a question about graph coloring. So the question here is, if I have a graph with chromatic number chi of g, what's the smallest partial coloring of g using chi of g colors, or at most chi of g colors, that extends to a unique chi of g coloring of the entire graph, right? So formally, I'll call some subset a Sudoku set if it has a uniquely extendable coloring like this, and then define this parameter, the Sudoku number, which is just the smallest Sudoku set that you can find. And this is gone by many names over the years. We chose to follow this recent paper, which called it Sudoku set. So it's maybe a bit unfamiliar. So I think some examples can help. So for one, if G is connected and bipartite, so it's two colorable in particular, and actually uniquely two colorable, the Sudoku number is 1, because once I make one of the partite sets say red, like you can easily see that there's only one way to extend that. On the other end, the complete graph, you need to color n-1 vertices before you determine a unique coloring. And then in the middle of these two, you have odd cycles. So basically here you can think of, you need to color half the vertices basically, and you can do it by coloring every other vertex to force the coloring. Not much, well, at least before this, was known for random graphs, and we thought we could say something that was a bit ambitious, at least the plural random graphs statement, but we said something about a random graph, which is the random 3 regular graph. And so here throughout this GN3 will mean a graph drawn uniformly at random from all graphs on n vertices that are deregular. And yeah, here's the result we proved. So we showed that AAS, meaning with probability tending to 1 as n goes to infinity, the Sudoku number of GN3 is at most n over 3, basically, asymptotically. And here I should note that it's not too hard to show that the chromatic number is 3 AAS in this case, so we're talking about 3 colorings. And the proof, which I won't prove it, I'll just hopefully show you some pictures which demonstrate what happens, but the proof is essentially by designing an algorithm which simultaneously colors GN3 with 3 colors and also builds this Sudoku set at the same time that forces the coloring. So before getting to that, I should talk just for a second about lower bounds. So here we found this deterministic result actually. So this applies to all 3 regular graphs with chromatic number 3. And it says on n vertices, I should say. And it tells you that for those graphs, the Sudoku number is at least n over 4, basically. And we tried for quite a while, actually, to move the bound off of n over 4 for random graphs, but we couldn't. So we just conceded defeat, basically, and conjectured that this is maybe correct. So we're still working on this. I think it's interesting, but really have nothing towards a proof in this case. Okay, so yeah, now I'll show you some pictures, hopefully, which kind of outline how this algorithm works. The first step is to use kind of a common trick in random graphs, which is to replace GN3, which can be somewhat complicated, with a simpler model. So here we're essentially decomposing the random 3 regular graph has a Hamilton cycle on n vertices unioned with a uniformly random perfect matching on the same vertex set. And so these don't have the same distribution, but they satisfy something weaker, which is contiguity. And this, for our purposes, just allows us to transfer AAS results between the 2 models. Because we're after something that holds AAS, we just use this. So for the rest of the talk, I'll say GN3, but I really mean this model on the right. And the reason we use it is because it gives like a natural ordering that you can use to process vertices in an algorithm. So here, I'm just thinking of, like I have the cycle H available to me beforehand, but none of the matching revealed. So that's kind of how this algorithm is initialized. And what I want to do is try to do 3 things at once, really. So I want to reveal the matching, color the vertices, and also build this set. So all at the same time. And I just go in order of H. So starting on the left, the first thing I do is I reveal the matching, but only partially. So what I've done here is I see that this vertex has a forward edge, meaning it goes like clockwise, I guess, around the cycle. But I want to leave it for now random. So I just like write in my book that it has a forward edge and save that for later. The coloring rule is basically color randomly. So I just color randomly with any available color I have. So this guy got red. And then the last step is just to say, well, there's nothing around here that says that this vertex should be red. It's like totally unconstrained at this point. So I just kind of give up and say, well, because he's not forced to be red right now, I'm going to put him in this Sudoku set. So my goal is to build a small Sudoku set. So this is kind of a very naive way of doing it. But yeah, the rule is if I'm not forced, like when I'm colored, I go in the set, right? So the same thing happens here. So now this guy is constrained a little bit, like he can't be red, but he still could be green. So he also goes in the set. Same thing here. Something interesting happens at the 4th vertex. So now I find a backward edge. And when this happens, I actually want to say where it goes, right? So I know it's going somewhere behind me, and it has to land among these vertices which are already colored. So I just sample that randomly. Right? I say where it goes. And in this case, I'm happy because it hits a red vertex. He already had a green neighbor. So the color here is actually forced to be blue, right? And I'm happy because I get to skip him. Like I don't have to put him in the set. Yeah, I just move on. So I carry on in this way. Here's another kind of interesting thing that can happen. So I can have this edge going backwards again, but I can also be unlucky in this case. Like he had a green neighbor here. He got another green neighbor, which doesn't help me, right? It doesn't force the color there. So unlucky again, he goes in the set. And we just do that until the end. So there's some minor details about what happens when I wrap around the cycle, right? So at least here I always have a color available, but that might not be the case for like the last vertex in the cycle. So maybe you can just take my word for it that this can be dealt with in another way. That's not too bad. But now I want to think about like how big is this set that I built? Like how many vertices do I circle basically when I do this process? And the observation is that only bad vertices get kept in the set or get put into the set. So those are vertices with forward edges. Like I'm sort of hopeless on those, so I always put those into the set. Or vertices with bad backward edges, like this one was, where I go backwards but still don't force a color. And we just want to compute basically how many of those do we get. So the forward edges is actually easy. It's deterministically I'll encounter n over 2 of them because there's n matching edges. So that's easy. The second one is actually random though. So here's a way you can think about computing it. So at time I, like I remember I said at the beginning, I sort of keep track of when I reveal a forward edge but don't land its neighbor. So at time I want to know how many unmatched red, blue, and green vertices do I have. So that's these x's. And I make, for now, like a heuristic assumption that these are all basically equal as the process goes. So it's reasonable, I think, to assume this because we're coloring randomly. So they should, I mean, this isn't a proof, but they should be close to equal. Then if I am at vertex I and he has a backward edge, so I condition on having a backward edge, the probability that it's bad is like a third, basically, asymptotic to a third, because there's always one color that I don't want to hit with those edges. And from this and some concentration inequality, you get that the number of bad backward edges should be this AAS. So there's n over 2 of them total, a third of them are bad. And this actually gives an upper bound of, so if I add this to n over 2, I get 2n over 3, which is not what I told you in the theorem. But without going into the like gory details of what happens here, we basically extend this idea. It's not much more complicated than what I showed you, but we extend it so that we only have to take every other bad vertex and put it in the set. And basically the idea is if I find a bad vertex at some step, I just don't give up on it right away. I try to force him using some vertices later on. And we can do this. Yeah, it gives n over 3 as the bound. So the crucial thing is still that this balance condition obtains for the whole process. But now it's I mean, I haven't told you how this works, but it's much harder to justify in this case because we sort of rigged the system so much to extend the algorithm that it's less random than it was before. So the proof, and I think I'll just stop maybe on this slide, to analyze the algorithm like rigorously, we basically need to understand the trajectories of these XCIs. And to do that, we use differential equations method. So the idea is we sort of assume that their trajectories, like after I rescale them, are closely modeled by some continuous function that's the solution to a differential equation. And maybe the one sort of, so this tool is used a lot for problems like this. Maybe the one like novel thing in the proof is that we actually over long-ish segments of the algorithm approximate it by a Markov chain, and then derive the things we want by saying that chain mixes and using the stationary distribution. So yeah, I think I'll stop here. Here's a summary, some future directions, but thanks so much for listening.